At the end of this video, I hope that you can list and compare the distinctive properties of ionic and molecular compounds, write the Lewis structure for a polyatomic ion given the identity of the atoms combined, and other appropriate information. Chapter 6, Section 3, a comparison of ionic and molecular compounds. The force that holds together ions in ionic compounds is a very strong overall attraction between positive and negative charges. In a molecular compound, the covalent bonds in the atom making up each molecule are also strong. But the forces of attraction between molecules are much weaker than the forces of ionic bonding. This difference in the strength of attraction between basic units of molecular and ionic compounds give rise to the different properties in the two types of compounds. The melting point, boiling point, and hardness of the compound depend on how strongly its basic units are attracted to each other. Because the forces of attraction between individual molecules are not very strong, many molecular compounds melt at low temperatures. Conversely, because of the strong forces that hold ions together, ionic compounds generally have higher melting and boiling points than do molecular compounds. Also, they do not vaporize as easily at room temperature as many compounds do. In fact, many molecular compounds are already completely gaseous at room temperature, which can be seen by observing the data table on the screen now. Ionic compounds are hard but brittle. Why? In an ionic crystal, even a slight shift of one row of ions relative to another causes a large buildup of repulsive forces, as is shown in figure 6-17 on page 179 of your text, or on the screen now. These forces make it difficult for one layer to move relative to another, causing ionic compounds to be hard. If one layer is moved, however, the repulsive forces make the layers part completely, causing ionic compounds to be brittle. In the molten state, or when dissolved in water, ionic compounds are electrical conductors because the ions can move freely to carry electrical current. In the solid state, the ions cannot move, so ionic compounds are not electrical conductors. Many ionic compounds are soluble in water. During dissolution, the ions separate from each other and become surrounded by water molecules. Other ionic compounds do not dissolve in water, however, because the attraction of the water molecules cannot overcome the attraction between the ions. You can also identify a compound as ionic through a series of simple tests. First test, you can examine the substance. All ionic compounds are solid at room temperature. If the substance is a liquid or a gas, then it is not an ionic compound. However, if it is a solid, then it may or may not be an ionic compound. Another test you can do is tap the substance gently. Ionic compounds are hard and brittle. If it is an ionic compound, then it should not break apart easily. If it does break apart, the substance should fracture into tinier crystals, but not crumble into powder. Another test is to heat a sample of the substance. Ionic compounds generally have high melting and boiling points. If the substance melts, use a conductivity apparatus to determine if the melted substance conducts electric current. Ionic compounds are good conductors of electric current in the liquid state. Lastly, you can dissolve a sample of the substance in water and then use a conductivity apparatus to see if it conducts electric current. Ionic compounds conduct electric current when dissolved in water. Polyatomic ions. Certain atoms bond covalently with each other to form a group of atoms that has both molecular and ionic characteristics. A charged group of covalently bonded atoms is known as a polyatomic ion. Polyatomic ions combine with ions of opposite charge to form ionic compounds. The charge of a polyatomic ion results from the excess of electrons, resulting in a negative charge, or the shortage of electrons, resulting in a positive charge. For example, an ammonium ion, which is the most common positively charged polyatomic ion, contains one nitrogen atom and 4 hydrogen atoms and has a single positive charge. Its formula is NH4+, sometimes written within brackets to show that it is a group of atoms as a whole that has the charge of 1+. The 7 protons in the nitrogen atom plus the 4 protons in the 4 hydrogen atoms give the ammonium ion a total charge of 11 plus. An independent nitrogen atom has 7 electrons, and 4 independent hydrogen atoms have a total of 4 electrons. When these atoms combine to form an ammonium ion, one of their electrons is lost, giving the polyatomic ion a total negative charge of 10 minus. Lewis structures for the ammonium ion and some common negative polyatomic ions, like the nitrate, sulfate, and phosphate ions, are shown on the screen now. To find the Lewis structure for a polyatomic ion, follow the steps of sample problem 6-4 on page 174 of your text, with the following exception. If the ion is negatively charged, add to the total number of valence electrons a number of electrons corresponding to the ion's negative charge. If the ion is positively charged, subtract from the total number of valence electrons a number of electrons corresponding to the ion's positive charge. At this point, I hope that you can list and compare the distinctive properties of ionic and molecular compounds, and write the Lewis structure for a polyatomic ion given the identity of the atoms combined and other appropriate information.